Conventional models of nuclear fission explain energy release as the kinetic energy of fission fragments, governed by Einstein's mass energy equivalence, E equals mc². In this view, high-energy fragments plow through the surrounding lattice, displacing atoms and creating linear damage trails. However, this perspective struggles to explain several violent, complex, and three-dimensional transformations observed in irradiated nuclear fuel. The exploding mass defect hypothesis offers a bold alternative, that fission releases energy as a localized microscopic explosion, generating a spherical quantum shockwave. At the core of this idea is the notion that the mass defect explosively transforms into a new form of matter. Specifically, the missing mass undergoes volumetric expansion, converting into a super-thin, space-filling form of matter that permeates its surroundings. This process is not just energetic but physical, leaving behind structural consequences that can be observed. Each fission event becomes a micro-detonation, and the resulting matter contributes to both local damage and possibly broader physical effects. Evidence from spent nuclear fuel supports this interpretation. Point defects and amorphous zones are better understood as the debris and quenched molten cores of countless microexplosions, rather than the result of particle collisions. The high burnup structure, HBS, a porous, pulverized region at the pellet's rim, is reinterpreted as the cumulative outcome of overlapping spherical shockwaves. Its sharp boundaries and ultrafine grain structure align more naturally with explosive fragmentation than with gradual thermal processes. Additional support comes from the redistribution of fission products, especially volatile elements like cesium and iodine. Their rapid migration and clustering in cracks cannot be fully explained by diffusion. Instead, extreme temperatures from microexplosions likely vaporize and violently expel these elements. Likewise, metallic nanoparticles, often thought to form slowly through nucleation, are seen here as the rapidly condensed ash of the explosion. Macroscopic cracking in spent fuel is also consistent with this hypothesis. Rather than being caused solely by thermal stress, the widespread three-dimensional crack networks resemble fatigue from repeated internal shock waves. Each fission event contributes to cumulative mechanical stress, eventually fracturing the material. The hypothesis also makes unique, testable predictions: spherical, not cylindrical, damage zones, pressure-induced polymorphs of UO2, and nanocrystalline crater structures from ultra-rapid cooling. Advanced techniques like cryogenic TEM and femtosecond X-ray diffraction are now capable of detecting these signatures, providing a concrete path to validation.